All right, so in this lecture we are going to be learning about another integration method or another technique to take integral. So I highly recommend that this lesson or this lecture is to be viewed or to be learned after you have learned the substitution method as another technique in finding an indefinite integral or finding an antiderivative. Okay, so here we go. It's the integration by parts technique right here. Okay, so the technique itself, yes, it's named the integration by parts technique, but let's not be too worried about the way how it's named, especially what it means by integration by parts, because right now, of course, as long as you arrive at this video lesson, you are on your way to learn the different techniques to take integration, to do integration. But so what does it mean by integration by parts? We will explore that as we go along, and then at the end, somewhere near the end of the video lesson, I am going to be able to explain what by parts mean. Okay, so I am now going to introduce a demo problem, or a problem that promotes the situation, the problem that motivates our thinking into looking for a new technique for here. Okay, so to start out as a demonstration or just an introduction problem right here for you to understand, we need more techniques other than just the substitution. Well, substitution methods we have learned earlier have done a lot of the problems for us already, but by the time that you have learned the substitution method, you can only find, in my experience, you can only solve about anywhere 80 to 90% of integrals out there. Okay, and so with this technique adding on top of what you've learned about the substitution method, then we are allowed to find integral problems for up to maybe 95%. Okay, I've never had a chance to sit down and really count how many problems there are out there. And in the world of taking integral problems, there is a limitless the sky out there about all of these problems. So let's get a look at this demo problem right here. So let's say we want to evaluate. Okay, but this problem is not a formal example yet. It's just a problem that I'm bringing up to promote the idea right there. Okay, to introduce the idea. So how about at this point, anyone in the learning about at this point in anyone's learning, then you are well familiar with this symbol. So this is indicating that we want to find the indefinite integral, or another way of saying it's the antiderivative of. Let's look at the function as following. How about x times natural log of x dx. Okay, so with this problem, let me spend about a few minutes to attempt solving this problem using the substitution method. I mean, I'm not saying that it's entirely impossible to use substitution method, but will substitution methods work fine? For me, myself, I gave up using substitution method for this problem because it's way too challenging for me. But who knows? There are viewers, there are students, there are mathematicians out there who are creative enough that can pull through with this problem using substitution methods. But you can substitute u equals x, okay, and then your problem becomes a du equals dx. So as far as substitution, that becomes u. And the natural log of x becomes natural log of u, and the dx becomes a du. And so you're not getting anywhere. So this method of substitution is not working for us. Well, then if you have a chance to review my substitution method, I kept saying there are no right or wrong substitution methods. So in that way, you can also substitute u equals natural log of x. The point of substitution, as you have seen that from substitution methods, is that we're trying to substitute a somewhat complicated expression to make it simpler, to turn it into a simpler expression. But then consequently, we have to write a lot of things in terms of the new variable u right there. So in this case, I see u equals natural log of x as another substitution choice. So du is going to equal 1 over x dx. So allow me to go skippy with the steps here, because as I already said, I highly recommend that this video lesson is to be viewed, is to be watched after you have already learned about the substitution method. So at this point, if we're looking back at substitution method, allow me to assume that you viewers have already had some certain experience with the substitution. So there's no need to go too far into the steps here and give all that explanation. So natural log of x is replaced by or substituted by the u variable. And so the substitution is going to happen as following. Natural log of x becomes u. X did not get a substitution, so it stays. Okay, dx, now du equals 1 over x dx, so that means du times x equals dx. And so now we can take this relationship and substitute for the dx here. So dx becomes x times du. And so here we're looking at x squared u times du. But so I'm sure there will be way to find, there will be way to substitute the x squared away, but I'm starting to sense that it keeps getting lengthier and lengthier and not getting me anywhere. But if any viewer is not so convinced that I stopped too soon, then yes, here's how we can handle it. If u equals a natural log of x, then x equals e to the u. Okay, and so x equal to the u right out from this relationship that we chose as a substitution expression for u. But so that means now I can bring that e to the u and substitute into my current leftover old variable x. So here we're looking at e to the u squared times u du. And so we're looking at consequently, that brings our problem to another integral, u times e to the 2u du. So we got out of the natural log, but in the end, and it's a brand new integral, but completely in terms of the u variable. So it looks like this thing here is ready for being integrated. However, if we're looking further, is it any better for us? Is it any easier for us? After the substitution, did we create for ourselves anywhere an easier integral to handle? Obviously not. And here we probably kind of have to lead ourselves into another chain of substitution. And so I brought up this so that anyone can understand that at some point the substitution method, either it's too challenging. I admit that on this path I already gave up, and I'm not seeing anywhere we can go. Maybe there are viewers out there who can pull through with something like this, but I'm not patient enough. Okay, and so in that way we are now under that big huge motivation to look for another technique, and that's where the integration by parts as another technique coming into as an extra addition, okay, to all the techniques, so that allows you, that empowers you to find be able to find more integral problems. So I am going to swing back to the earlier board. Now, as you have already seen in my quick demonstration, it didn't get us, at least here on my board here, it didn't get me anywhere from using the substitution method. And so I am going to forget about this technique for using substitution method. We are still doing a little bit of substitution, but we're going to take the substitution and approach in a completely different way. And that is the reason why I am highly recommending anyone, and I highly recommended earlier in the beginning of the video lesson, that this technique here should always be learned after you have learned or have had some experience with the substitution method. Okay, so before I really get into any of that, let's take some good observation. And still, I did not explain at all what it means by doing an integration by parts technique. We will get to that. So right now, let's have a closer observation of the problem right here. Now, I've had another video earlier, before you arrived at this video. I've had another video lesson to explain, the relationship or how the dx part here, this differential is connected to all the other ones. So in this overall integral problem, this is what I recognize. There's a function, namely x, that's one function, being in a product with a natural log. So natural log is one function. Okay, algebraically, I've had students mistakenly think of that as an ln times x. This is an algebraic flaw right there. So don't go that way. Natural log of x is one function. It's a natural log operation on over that on top of that x variable. So natural log of x is one function. The x itself is another separate function. And then all of these stay in a product with the dx differential. So altogether, we're looking at a product here. This x, natural log of x dx right here is a product of three separate factors. In other problems, there could be other the things, but there's always a dx, as you have already know. And then there's going to be some products of some two other functions. Okay? So that's the first foundation that I want to set for anyone before you start heading out to apply your integration by parts technique. Okay? And so once you clearly recognize the function, the overall function that you're integrating, that you're trying to find the antiderivative or you're trying to find the integral, has these two functions aside from the dx expression right here, then the next step now is that among any one of these two functions that you have recognized, you are going to make a substitution. Yes, we are going to make a substitution again. But again, after we make that substitution point, I am going to use that in a completely different approach. Okay? And so we have, at this point, starting from scratch, I always recommend my students, do not worry about what's a good choice, just pick one, okay? And I'll show you, after you picked one, what do we regard the rest of them as. So here I need you to follow with my experience right here. So how about just right now as my choice, I'm going to substitute u for natural log of x. Okay, so once again, let's look back and quickly recap things before we keep going on further. So observation told us that our function, the big function that we're trying to find the integral here is a product of two separate functions. And then of course it's the whole function here is in product with the dx expression. Okay, but the entire expression here inside of that integral sign is really a product of three separate things. Okay, and so just now I made it clear that, and I can say it clear again, it's a choice that I picked this one. Okay, I'll pick this one, and we will never substitute away the d expression here. We will only substitute either one of these functions like that. Or there could be more than two functions here, but we only pick one. Okay, and treat the so we only pick one. Basically, that's what I'm trying to say. And so now, here's the next critical step that I want you to understand. Once you made your choice, and respect your choice, okay? Do not worry about is it a good choice or a bad choice, okay? What matters is will it be a working choice, okay? And then, of course, as we progress further, we will kind of summarize our experience and come up with a rule of thumb, a good rule of thumb for you to be able to pick a good choice, a working choice, okay? So u equals natural log of x. So that means once you made that choice, picking this to be u, then everything else, including, now you hear my word, everything else outside of that one, you substitute it away. Everything else meaning the x and the dx. So I also said, including the d expression, okay, in a product, x dx. Because in the entire expression at the beginning here, then after we substitute this natural log of x away for the u variable, then everything else aside from that natural log of x is this x times dx, or x in product with dx. Okay, and so now I'm going to regard to this as another, how about a dv. So I've had another video lesson to explain these are all, at this point in your learning, in your majority of calculus that we call any of this, the dx here is the differential of the x variable in our expression, and v here, think about there's a function v of x, then dx is the differential of x, and the dv right here is the differential of the variable v. Okay, and so x times dx can be regarded as a differential dv, or think of that as simply another derivative. Okay, and so now that's what I was trying to explain. We simply made a choice among these functions available right now, right out from our beginning problem. Then I made a choice that natural log of x gets substituted by a new variable u. But then, once I substituted that as a choice, then everything else in this beginning product, aside from this natural log of x, is being regarded as a dv expression. And of course, try to always maintain this as a product, as a remaining product that, without the natural log of x in there, okay, without the one that you made your choice being substituted away. So now, in that way, let's explore a little more. So it makes sense clearly that if u equals natural log of x here, and u is a function of x, then in that case right here, think about it this way. Yes, du dx, this is the derivative. We are doing integral calculus now, but we still have to do a lot of differential calculus, the work at taking derivative. So du dx is the derivative of the function u in terms of x. But now in your understanding previously, after the calculus, after you finish your whole course of differential calculus, then you also well aware that this symbol here is not only a symbol for derivative, it also means a fraction of two differentials. Okay, the du differential and the dx differential. So du dx for now as a derivative. So derivative of u in terms of x is 1 over x, because that's the derivative of natural log of x. But this means further that just now I said we can now understand this du dx as a fraction of the two differentials. And so we can rearrange this as a du to equals 1 over x times dx. Okay, and so I noticed that the way how I present this is a little too tight right here. So let me erase this and rewrite that a little further to the side, because I want to keep all this side here on one end by itself. So if u equals natural log of x, du dx started out as a derivative of the function u in terms of x. And yes, the derivative of natural log of x is 1 over x. And that leads to, as a next step, I can rearrange it as a differential, an equation that involves the differentials. How's that? Okay, and so that now is a 1 over x dx. So this is an equation of the differentials. Okay, and then let's hold on to that problem. And then I will come back to this side of the board and fill in what's missing with this part right here. Okay, but now, so it's part of it. It has the substitution, but I did not use a substitution. So there's still some similarity with the substitution we have done back in the substitution methods, but that's about all I'm doing. So for now, I'm going to navigate to my other side of the board. So here's what I'm seeing. The beginning problem, x times natural log of x in product, okay, and in product with an extra dx right here. I substituted this away to become a u, and so after all that fancy work right there, then our problem here is being recognized now as a, okay, this is a u, that's for the natural log of x. And then the entire x dx right here was regarded as a dv. Okay, and once again, back on my other board, the reason I can make that argument was that because, see, as I said earlier, once we made our substitutions, we made our choice to pick one function among these that we found available in our beginning problem. After we made our choice and substituted that away, then everything else as a product, but the product of everything else, including the dx, is regarded as a dv, and that's how the beginning problem is now recognized in a new expression, as a new expression. It's an integral of some function u, but multiplied with some differential dv. Okay? All right, so now, still, I did not explain what integration by part is, but at least now I can introduce for you the technique of what to do when you're calling this technique the integration by parts technique. So the essential or the schematic, the theme of this integration by parts technique is that once you have identified any of your starting problem as a u dv, okay, then we have the following formula. u dv, as long as you, so this u dv, I want my viewers to understand that it's entirely on your choice to re-express that. But once you have identified your u dv from your beginning problem, then here's what we can do as a formula. And this is the whole idea of the integration by parts. And then I will explain why we call that integration by parts later. So anytime that you have successfully landed your beginning integral problem into the u dv expression, then the formula to proceed is as following. This integral equals u, that function u that you substituted away, times v. So this v now is all of a sudden being a little mysterious. I will explain that. Okay? Times with some function v, and then minus as a formula an extra integral that we have now produced for ourselves, the formula produced, v du, v times du. So this is a formula, the essential and the core formula in your integration by parts technique. It's done by following a formula like this. Immediately as soon as you have recognized your starting function to be in the form of a u dv. Okay? And so, and I really made it to be understood for my viewers to understand in a way that u dv is completely on your own control. Okay? You have your own choice, your own control on how to turn your starting function, your starting integral problem into a u dv expression. And once you've had that, then the formula to follow there is that u dv, that integral of the u dv will equal u times v as a product. And then we're going to subtract the integral of another, we're going to subtract another integral of a v times du. Okay? So now allow me to explain what this v is. Magically, where did that come out from? Where did that v come out from? Okay? Everyone at this point, anyone viewing the video at this point has understood what that dv is and where that u came from, okay, and where that du came from, okay. But now magically, what's the v and where did that come from? All right, and so back in my beginning board, you see. So let's quickly flash back a little bit. So eventually, the du this is the du expression that we will be using right here. Du as a differential is 1 over x as an expression, 1 over x dx. That du will eventually be substituted for this. Okay, but that's going to be the story of a little bit later on. So now let's find out and let's see some explanation of where the v come from. So if you're looking at this dv right here, right now it's a differential, right? And then it equals as an expression x times dx. So to find v, really, to find v, that all that is now we are going to take the integral, because see, dv is another, now I call that formally the differential, but it's closely, or it's also directly related to the derivative, and you can simply think of this as the derivative of v, okay, in the differential expression. Okay, so if this is the derivative of, we already had the derivative of some v function. So to find v, that's the whole reason why we've learned through that video lessons earlier about what antiderivative means. An antiderivative is this integral work that we're doing. And so v here equals, now we just simply take the antiderivative or the indefinite integral of x dx. this is now a very simple integral problem to be done right here. And so this is going to be 1 over 2 x squared. Did I forget something? I don't think so. Now, the reason I said that, because when you were viewing that in my other video lesson about how to take antiderivative and how to find an indefinite integral in general, antiderivative up until this point of our learning is an indefinite integral. But I've been yelling out loud that do not forget the add c, the plus c. Okay? And so some viewers are starting to worry whether I've forgotten something. I have forgotten something. Nope, I did not forget anything. Now, when you're just taking an antiderivative as a small step in your integration by parts work, I repeat, anytime that you are doing this small little integral work, indefinite integral work, or the small antiderivative work right here, you don't need to have the plus c. Okay, you don't need to have, and this is the only exception here. We don't need to have the plus c here. Okay, it's just all to keep things simplified. It's proven that it will work the same whether you're having the c, the plus c or not. But having the plus c is making it more problematic. Okay, harder to handle, even though it turns out the same result. So in that way, it's proven that it's completely legal to leave the plus c out in the small step that required us to find the antiderivative of this dv from right out from that dv. Okay, so there we go. That's our v. Our v is here, 1/2 x squared. Okay, and then our du is that expression 1/2 dx. I mean 1 over x dx. All right, so let's see how I can put all the pieces in place right now. Allow me now to erase this formula, or maybe I'm gonna write this part on the right hand side of the equation to that next line right here, to that line, and then I'm gonna make some space for that. And so our expression has been recognized. Our beginning problem was already recognized as a u dv, and so now the formula says we need this integral will equal u times v, okay, minus an extra integral v times du. Okay, so let's see now how I put the pieces together. U was that chosen one, so it's natural log of x, and v is this 1/2 x squared. So this 1/2 x squared here is v. So that means when we're putting that together as a product, as indicated, as instructed by the formula, then we're looking at 1/2 x squared times natural log of x. See, u times v. We follow just strictly with the formula. Okay, and then I am going to subtract. And then that subtract what? Subtract an extra integral that we have produced with the formula. So really the formula produced that for us. And big thanks, big credits to whoever derived this formula right there for us to use in these days. Okay? And so v again, and it's a product of course. Okay? So v times du. So v was that 1/2 x squared. So I am going to put that in. 1/2 x squared. Okay? In product with du. But this du, we found that du is equal to this differential expression right here, 1 over x times the differential dx. Okay, so I am going to take this exact expression right here, 1 over x dx right here, and substitute that for the du. So it's not exactly the method, the substitution method, but it still requires you to be able to operate with the substitution and turn a substitution into a differential expression like that. Okay, so in that way, du now, okay, can be regarded as 1 over x dx. I put parentheses around to indicate that we just now substitute this for the du right there. All right, so look at how beautiful this is. We have already had one term being 1/2 x squared natural log of x. So keep in mind, in the next step or starting this step, we never had to worry about this first term anymore. But we do have a little bit of integral, another little bit small integral to worry about. 1/2 x squared times 1 over x times dx. Isn't this a lot simpler as a little integral to handle? You can bring the 1/2 out front as a coefficient, and x squared cancel with 1 over x gives me just simply x dx. Look what we have produced for ourselves. Okay, and so 1/2 times the integral of x dx. So that now gives us all right, so at this point I have left these here long enough so to continue my work here. And I'm still going to leave this part here at the bottom so that we can reference back at some point later. But now continuing from the earlier step. So now our problem will become, okay, so from the very last step right there, from this, so we never have to worry about that because that one is done, that term is done. It's 1/2 x squared natural log of x minus 1/2. What matters for us now is simply find out what that integral of x dx is. Okay, and so now we're looking at 1/2 x squared natural log of x minus 1/2, that's the coefficient, but multiply with another 1/2 x squared. With this one here, your answer needs to plus c. And so no more integral. We have found the answer to all integrals. And yes, we should multiply these two coefficients together. So as an overall, as a final answer, 1/2 x squared natural log of x minus 1/4 x squared plus c. And this is your final answer. This is your final answer. Okay, all right, and so ever since the beginning of learning about integral, I highly recommend, I put this answer in a box a little too rushed, but I highly recommend anyone viewing the video, anyone learning from this lesson right here, to take the derivative to ensure that this is your correct final answer, okay, because taking the derivative is the only way to check whether you have had the correct answer for an indefinite integral problem. Okay, and so now I am going to erase this little word. And we can see that for one among a few rare occasions, I am going to save you time right there. I am going to do another derivative problem right out from this answer, so that to ensure that our work was done correctly. So it's a product here. So first term, when we take the derivative, first term here, the derivative on this product rule says, okay, 1/2. I shouldn't even have to, or maybe I should leave it there, times 2x times natural log of x plus, okay, that's just part of the product rule that we're trying to find the derivative on this product right here as the first term of our final answer. Okay, so 1/2 times 2x plus natural log of x, and then plus 1/2 x squared times 1 over x. This is the derivative of our natural log of x function in that product. And then minus. So now 1/4 times x squared right here gives me a 1/4 times 2x as derivative. Okay, and then the constant term here, after we take the derivative, it becomes 0. So this is our derivative. And then some terms cancellation and some common factor cancellation. It gives us x, because the 2 and the 2 here cancels out, x times natural log of x. These two multiply, and the x squared cancel with that x. So it gives me a plus 1/2 x. Okay, and then minus this 1/4 times 2x right here. The 2 cancel with the 4. It gives me a 1/2 x, but minus 1/2 x. So these two terms cancels out. These two terms cancel out. And so in that way, look at our final answer. We came back to the beginning problem, x times natural log of x, that we've had at the beginning. that we had at the beginning here. So we were trying to find the integral of that, or the antiderivative of that. And then we came to an answer. We came to an answer. And then we doubt if we made any mistakes. So the only way, the perfect only way to check whether we have found the correct antiderivative is to take the derivative of that. And we did land back into that beginning problem, x times natural log of x. And so now we know that this is our correct final answer as the indefinite integral of that beginning problem, x times natural log of x, or this is the antiderivative. All right, so this is only a demo problem, but it shows you how useful that is for the integration by parts problem. So the essential formula in the whole work of doing integration by part is this formula to remember. It's this formula. And so, again, I am highlighting this formula right here. Being able to express your beginning problem into a UDV, that's under your own control. And so I hope I pointed out enough details that you're always starting out with a function that's having more than one little factor in it, and each of those little factor is again another simple function itself. And then we picked a choice. I said that earlier. We picked a choice. So in my experience, I picked natural log of x as a choice. Okay, and then we re-express our problem here, our beginning integral as a u and dv. What's critical to remember here is that once you've made your choice for whatever you chose to be the u, that's the first step. Then the next step is everything else aside from the u that you have already substituted for, that you have chosen, then everything else as a product, including that d expression right here, will be regarded as your dv. And that's how you can successfully see your beginning integral problem as in a udv form, in integral of a udv form. And then after you have successfully identified your integral problem in a udv form, and this is the formula for that. Okay, and so now I am going to swing back to the other board right there. And we're as far as solving the problem, we're done solving it. We're done solving this particular problem. Okay, but let's give some further insight about it, and let's look a little further into that. We need to have some thorough understanding before we head out for some formal example, and before we even come up with some good agreements about a good rule of thumb to how to make a good choice. Because remember that the first big step is to pick a u right there. And so now let's look back at the problem one more time. X times natural log of x dx. It's x as a function times natural log of x times a d expression. Okay, and then I pointed out earlier, we got in this particular problem, aside from that dx expression, we got two functions right here, and I made that choice earlier, and it was successful. So what if we chose u equals x? Okay, what if we substitute this entire function away? And so if we chose that x to be substituted as a u, and x itself, even though it seems like it's just a variable, but it's a function itself. It's a function, the simple function x. So if we chose that function in this product to equal u right here, then again, everything else in this product, aside from our chosen one that was substituted away, then everything else is, of course, natural log of x dx. Everything else is being regarded as a dv. Okay? And so if we went this path right here, if we went with that path, then on the u side right here, on the u equals x, then of course du dx will equals 1, because that's the derivative of this simple function. And then re-expressing this equation in the form that involves the differentials, then I can now multiply both sides by dx, and that gives me du equals dx. Okay, and then now with dv equals natural log of x, dv equals natural log of x times dx, then finding v means to find v here, very similar work with, I mean, the structure remains exactly the same with how I've done that before. What's different here is that we have different choice substituted for u, and then different choice to be substituted and regarded as dv right here. But now once we've had our dv here, then v is supposedly found by taking this natural log of x. Okay. I'm not saying that this integral of natural log of x dx is impossible to find. I'm not saying that anyone learning through the integral calculus with me will eventually learn how to find this particular one. But believe me, at this point when you are still viewing this video lesson, connecting with earlier video lessons that I have delivered, then we have never found any solid technique to find this one yet. So in other words, up to this point, without learning, without knowing how to handle this integral natural log of x dx, then we got hung up right here. Okay, we got hung up right here. We don't know how to proceed further. That means this formula, it's still the same formula. We will never change the formula. But apparently, if we did that path, if we chose the substitution the other way around, and we produced these, then we got hung up right at the step where we're attempting to find that v right there, and so it was not successful yet. Okay, and so in that reason, so now integration by parts can be a bit challenging sometimes in a way and especially for beginners. It's challenging in a sense that sometimes it's a little bit difficult to make a good working choice of the u to start out with, because once you made a good working choice for the u, and of course set everything else, set the product of everything else, including the d as the dv expression. If that u substitute, that u choice of yours in the beginning was a successful one, then the rest is going to go smoothly. Okay, but unfortunately, if we set off our starting point right at with choosing a not so successful one, okay, I want anyone to have faith in your own path right there. You can choose and you can work harder. Maybe you work a little harder, but see, the more you work, the more you learn. So don't be afraid of an unsuccessful choice sometimes. That's how it happens to all the past mathematicians. And so if we ended up with an unsuccessful starting u choice right here, okay, then go ahead and try a different one. Okay, and so, but now in these modern day, for all students, since all of the famous mathematicians in the past have already come up with this good rule of thumb for us, and we're talking about countless of efforts that the people in the generations before us have gone through and passed down all that experience down for us. Here now, allow me to introduce for you this rule of thumb. It's not a proven method, and I'm still talking about within the integration by parts, but making the u choice could be a little bit challenging sometimes. So looking back at the experience from past mathematicians and from earlier generations that passing down on us, there's this technique right here that's not guaranteed 100%, but it will work. It will work a high chance enough. I mean, a high percentage of time enough. A high percent of time enough. Like, I mean, maybe 80% or 85% of time, or it could be up to 90% of time when you are working on an integration by parts problem. Then you can use this method. So, Liate, what is this method? Really, it's short for Liate. Is the L here came out as the shorthand abbreviation for logarithm. Okay. I right here is short for inverse, but intentionally inverse trig function. Okay. And then A right here is short for all the algebraic function. Okay. Meaning those powers of x, or those roots of x, those are all regarded as algebraic functions. Okay, and then the t here is an abbreviation for all the trig functions. Sine, cosine, tangent, cotangent, secant, cosecant, all of those fundamental trig functions. And the last one, the E here, is the abbreviation for exponential. Okay, e to the x, a to the x, 5 to the x, 8 to the x, 3 to the x, 1,000 to the x, 1/2 to the x. Okay, all of those are in the whole family of the exponential functions, the exponentials. Okay, so here's the idea. It's a good rule of thumb, and if you're reading this, so after I give an explanation of what these capital shorthand abbreviation here together, then now let me erase all that. Okay, if we're looking at the whole rule over here, if we're looking at that from the left to the right hand side, and it's indicating a certain order. So the one that's starting out from the very first left hand side right here is the one that anytime you're looking at your expression right here, anytime you're looking at when you are doing an integration by parts problem, okay, and a lot of time, big percent of times, that when you're looking at a product, that because the idea now is that any of your products that you are doing in an integration by parts problem comes as a product of two functions, and each one of these functions is a family among these. Okay, and so if you're looking back at this thing right here, you see there was this natural log which belonged to the L family, the logarithm, and then there's this x right here, namely x to the first power, and this belongs to the A family, or the algebraic family. Okay, and so if we're looking at this Liate rule right here, as I said, it's never been formally proven, but it works about 85 to 90% of times for those problems. There are still exceptions out there. Okay, but if we follow this scheme, so from the left to the right, it's indicating that whoever in this family should get the highest priority to be chosen as the U. So it's all about how we can successfully choose the U. So if you recognize throughout a good mix of all different functions, and any of your functions come from any of these families of functions, then I found L, so L has to come before A in this Liate scheme, right? And so in that way, my U, that's now makes sense why in the beginning when I introduced the problem, I chose U as a priority choice to be the natural log. Okay, so that shows me that this Liate is a good rule of thumb right here that's worked about 85 to 90% of times, how you can pick a good successful U, and once you've had your U, the rest is going to come out easy. Okay, all right, so now after all that understanding, okay, and you have seen some of some explanation about the Liate, and I'm not even sure how we pronounce that, but I've heard that from my past professor who taught this to me. He pronounced that Liate, so now I hand it down to any one of you learning from this. But anyway, so after we've learned about this, let's do a couple of examples, and now we're talking about having some hopefully solid enough technique so that we can handle the integration by parts as a technique, but then we have a good way, a good rule of thumb to choose to start out with our U choice, the U choice. Okay, all right. So now, and I have to have one more word before I'm heading out for an actual example over here. There is a whole world of creativity within these integration by parts problem. So the number of examples I offer in this particular lecture, or the number of examples being offered directly in this lecture, is very limited. But outside of this particular lecture, I will have discrete little examples that it could be some special ones, and it can also be someone that quite directly related to the Liate scheme right here. So in that way, keep checking back to see if I have posted some more examples. But I'll have about 2 or 3 examples in this particular video lecture, and then outside of this, I will have separate little lessons. On each one lesson is on one example. Okay, and the more time I have, the more examples I will be posting just on the integration by parts, and that's the plan for this. Because when you get into the learning about integral calculus, it's a very challenging job. I mean, it's a very challenging job to teach, and it's also a very challenging thing to learn like that. So, you know, both teacher and students have to work hard on both sides here. I'll keep hunting for more examples, for more good example and post, and then my students are going to keep, you know, looking through. The more you are willing to look out for more examples, the better you in good shape, and there will never be enough examples out there. So start relying on your own creativity out there as well. Okay. So now, in the first formal example here, in this particular lecture, so in order to order all of the examples, I call the first problem here example 1. So let's evaluate. Let's evaluate. All right. And I'm now going to call that part A. The integral of x times e to the x dx. X times e to the x dx. All right, so now here's how the Liate scheme is going to be useful for us right here. And if remember again, be open to your own creativity, because as I already said, this Liate scheme is only going to work for about anywhere from 85 to 90% of time within these integration by parts problems. Okay, but of course, for you to build your own confidence right here, I will start by choosing the example problems where throughout all of these problems it will work. But I don't want you to fall into that false understanding that this Liate is always going to work. Nope, it's not. There will still be exceptions to the Liate scheme right here. Okay, but at least let's have a look at our function right here. The function we have is x e to the x. It's the one function, but it has x times e to the x. So now if we're looking a little closer, there's x as one little function on its own, and e to the x. These two come out from 2 different families. Okay, so and then multiply with the dx. So of course, everything we're talking now is sort of like aside from the d expression. So x times dx. This e to the x is so clear. It's from the exponentials family. And then this x right here is x to the first power. It's a power function. So we can categorize this x to the first power as into the family of the algebraic functions. Okay. So now once you have identified within this product of the 2 little functions in this mix, when classes are still face-to-face, I keep referring this to my face-to-face student. This is a mix of functions from different families. I'm willing to also share that with viewers who learn from this video lessons right here as well. And so, but now as soon as we recognize that the family where each one of these came from, then clearly, you see, and in this Liate scheme from the left to the right, the further left, the higher priority it is. And so now A is to the left of E right here. Okay, that means now we're gonna get U equals X, because for picking the U choice right here, the higher priority is the algebraic family. Okay, so now that means my U choice is now having a clear answer for us. We should pick U to equal X. So the way how I see it, we're not substituting for the variable, and we're picking an entire function family and substitute that for a new variable. It still somehow requires anyone at this point to be comfortable with the substitution methods so that we can move on to the integration by parts. And that's why I highly recommended earlier at the beginning of the lesson here that you need to learn this lesson here after you have already learned about the substitution methods. Okay, so once we have made our choice that U substitute for this function from the A family, then everything else remains in the product aside from our U choice. So now, namely, I'm looking at e to the x dx, right? Including the d expression, the d expression. All of that there is regarded as our dv. And think of that as the derivative of some e to the x functions, but written in the differential form. Okay? All right, so now with the formal experience we have already, with the experience we have already learned throughout the demo problem, the motivation problem that we've had earlier, then if u is substituting for this function, this simple function x, then du dx equals 1, or now you can rearrange this derivative into an equation that involves the two differentials. So du equals dx. Okay? And then when you get fluent enough, you are allowed to even skip that and jump directly down to this. It all depends on how comfortable you are seeing it. Okay? And so now this dv, think of that as the derivative of some v function. And so if you have dv already known to be e to the x times dx, then we can find v by taking the integral of e to the x dx. Okay, and then again, remind yourself from that explanation I've had earlier in the demo problem, in the beginning introductory problem right there, that after we have found this successful indefinite integral, we don't need the plus c here. That's the only instance ever that you're allowed to skip the plus c. Okay, it's well proven. So here v equals the antiderivative of e to the x. For our learning here, we've been well familiar. It's e to the x. And again, we don't need the plus c in this case. All right. So now, on the other board, again, I need to remind anyone, once you have successfully identified your beginning integral problem as a u dv, then the formula we use here, that integral will be equal to u times v, once you found it, minus, and then the integral of a v du. Okay, so the formula produced a little extra integral for us, but the idea now is that this extra integral should be a simple one. Okay, and so that's the formula to highlight for today. And so now, again, our starting problem was x e to the x dx, and we have already found that this is u, or that here is dv. So in that way, see, this is u, this is dv, all of that there. And so there's no need for me to, repeat that u dv here. So I'm going to get straight into that, applying that formula. Okay, so I have made my u choice to be x, and I have found, after we identify what our dv was. Okay, so v was found to be e to the x. So in that way, u times v. Now I'm looking at x times e to the x. Okay, and I need to subtract, according to the formula, I need to subtract an integral of, now v is e to the x, so e to the x. But du, remind yourself, we found du as a consequence by letting u substitute for this function x. So in that way du equals dx. So we have two differentials equal to each other. So in that case, the differential du right here is now replaced by, or substituted by, the dx. Simply just that. Okay. And so now if we're looking at the two terms here and specifically focus to this integral, it's a very simple integral to find. So in the next step, and again, this first term was already done. So in the next step, we're just simply going to copy and paste that. So e to the x, x times e to the x, and then minus, and now e to the x as the antiderivative of that. And then, so here, this is our final answer to the whole the integral problem. Do not forget, plus c. All right, so this is how we have found our antiderivative or the integral of x e to the x dx. Okay? And so I want any of my students viewing this video lesson to pause the video on your own and go ahead and take the derivative of this to ensure that we went the right way. Okay? But I am quite positive that I have already arrived at the correct final answer. All right. And so now, let's clear out the board and look at another problem so that we can get a better hang of the Liate scheme right here, the Liate rule of thumb right here, to make it to make a good U choice for our integration by parts. So let's look at problem B right here. All right, so in our problem B, how about we're looking at x to the fourth times natural log of x, okay, dx. Okay, so in this problem, again, before we even get into it, and of course we are about to apply the integration by parts technique, and let's see how Liate right here can help us, guiding us into choosing a good U choice at start. Okay, so let's look at this guide right here. So there's x to the fourth power in product with ln of x, with natural log of x, and then in product with dx. So aside from this d expression, we have a mix of two functions. One of them is from the logarithm family, and the other one is a power function which came out from the algebraic functions family. And so now among these two functions, the L family, the logarithm family, comes with higher priority. So that means now when we make our U choice, we should, as a higher priority, we should choose U to equal natural log of x, the one that's at higher priority. All right, so that's the whole scheme, the whole idea about using this Liate guidance right there. Okay, and then from there, once we made our choice, okay, that's properly aligned with this guidance, then everything else. So in this product, there's x to the fourth, there's natural log of x, which was already isolated out and substituted away. So everything else now is just x to the fourth, including the dx. We regard all that here, substitute that as a dv. Okay, and so now that means here in our work, if u equals natural log of x, then the derivative du dx. But now you can start seeing this. You can also see this as a fraction of two differentials, du over dx equals 1 over x. And that, there we can rearrange this equation and turn that into du over, I meant to write du equals 1 over x, the derivative multiplied with the differential dx. Okay. And then on this side right here, once we have identified our dv, then v can be found by simply integrating this x to the fourth, this simple power function. So integrating x to the fourth in respect to x variable, okay, then that means our v here will be 1/5 x to the fifth according to the power rule for taking antiderivative. And we don't need the plus c here. Okay. All right. So now I am going to advance to the other board, and it's now time to put all the pieces together. All right. So now our beginning problem was an integral of x to the fourth times in product with natural log of x, and of course all in product with dx. And we now already recognize that this is u dv, and or I should have written that even though see, natural log of x, x to the fourth dx. See, all that here is u dv, And so the work now can be done as u times v according to the formula. So u was found to be u was found to be natural log of x right here. It was a choice, actually. I shouldn't even say was found. Okay, it's a choice which chosen to be natural log of x. V was found to be 1/5 x to the 5th. And so in that way, u times v here is going to give me 1/5 x to the 5th to be multiplied with natural log of x, straight out from the formula. And then I am going to subtract, okay? I'm going to subtract that extra integral according to the formula here. Then the extra formula, the extra integral here has the v inside of that integral and then the du. So let's see what v and du was. So v was that 1/5 x to the 5th, and the du is the 1/x dx. So if we're putting all these two together, okay, then we're looking at 1/5 x to the 5th, that's v, and du was 1/x dx. And now we have created for ourselves another another integral simple enough for us to, quickly get the answer. So, but let's clean up the terms a little bit. First term is just 1/5 x to the 5th, natural log of x, okay? And then the next term was an integral. You can now legally bring that 1/5 in front, okay, and take that as an x to the 4th dx, due to the fact that the x to the 5th here cancel with that other x in our 1/x fraction. Okay, and so now this is a very simple integral to take right here. And the first term outside of the integral, we don't need to do any further work for that. And so here's my final answer. 1/5 x to the 5th natural log of x minus, we have a 1/5 here, okay, but the antiderivative or the integral of x to the 4th is another 1/5 x to the 4th, and I mean x to the 5th. Okay, and don't forget plus c. So in the end, all together, we're looking at 1/5, okay, x to the 5th natural log of x minus 1/25 or 1/25, okay, x to the 5th power plus c. I am going to say that this is my final answer. But again, I highly recommend that public viewers or students of mine who are viewing this video, pause the video and go ahead and take the derivative of this final answer to ensure that we have landed into the correct integral and the correct antiderivative of our work. And so in the end, that's how it works. That's how we can apply the Liate guide, right, or the Liate guidance or scheme or whatever you can say it. But we use that as a good rule of thumb to have our good starting out u choice. Our good u choice as a start out right there. Okay, so now at this point, it looks like the whole time so far I've been focusing on indefinite integral because it is the way it is. I mean, the biggest challenge anytime that you are doing an integral problem, the biggest challenge is to be able to find the antiderivative, to be able to find the indefinite integral. And once you've had the indefinite integral successfully nailed down, then being able to find the definite integral is just the next step by applying the fundamental theorem of calculus. And that's why in my way to approach integral calculus, I tend to focus a lot, and that should be the same with any other instructors teaching integral calculus out there, that they need, including me, to focus mostly on all the techniques with working with the student to be able to teach student to find antiderivative successfully. And then once you've had that, doing the work that finds a definite integral is going to be just another small step above of that. Okay, and so now at this point, after you have seen enough examples, I am going to introduce an example where we're going to be doing a definite integral. And of course, the integration by parts technique is behind the scenes. Okay, and so All right, example 2. So we are going to evaluate, and in this example, I am going to only offer one problem here, and you will get a good hang of that immediately. So how about we want to find the definite integral from 0 to pi, okay, of the function x times sine of x. Okay, and so I have to mention a little bit. So this is a little bit about scratch work. Any standard calculus textbook out there introduce a formula as following. When you have a u dv and you are looking at at a definite integral like this. So just like my indefinite integral version right here, then the definite integral version has the two bounds, as you already knew up to this point. So back to what I was saying, many standard calculus textbooks tend to introduce the integration by part techniques on top of a definite integral problem as a fixed formula. It works, of course. Textbooks never lie to you. Textbook authors never lie to you. And I am still going to write this down. However, personally, I don't recommend my students to go this way. And I will explain that reason. Okay? You can just go, so the integration by part technique, say it's u times v. Okay, and then that's at that end product we are going to use that friendly, that familiar notation. Evaluate this from A and we evaluate this from B and subtract out the 2, and then we're gonna have an extra integral here being from A to B of v du. Okay, so it's a formula. It's good to know, and I feel guilty that I don't mention this. But in my entire lifetime doing this kind of problem, anytime it comes to doing the integration by parts with a definite integral, I tend to leave the formula aside. Actually, it has been working better for me that I can just separate the problem out as one separate indefinite integral, get it done fast, and then whatever the final answer, I will just apply the fundamental theorem on top of that. Okay, it's just the way how the formula is written. Yes, it's easy to understand, but when we actually apply it in practice, I never found very good luck with that in terms of efficiency. Okay, so I've introduced the formula here, but allow me to teach in a slightly different approach. Okay, so I'm not going to be too focused on showing how to use this formula here, right here, but I would rather focus on the problem as following. All right, so with our starting problem in example 2 right here, it's a definite integral accumulating from 0 to pi x times sine of x dx. And in my recommendation, as I said, I'm not using, I wrote down the formula, but I'm usually approaching that slightly differently. The way how I see that is I always want to handle the problem separately first as an indefinite integral. Okay, so there we go. So now I'm going to start out isolating out my indefinite integral problem first, completely without the worry about the two bounds right here. Okay, so I'm going to go, because in the end, whatever this is, it's just the antiderivative of all that is. So if this was lowercase f of x, recall from the fundamental theorem of calculus that we have learned. Okay, then in the end, we will definitely need the antiderivative, which will be essentially or importantly that indefinite integral. And then the overall answer here, as proven, will be evaluated from 0 to pi. Okay, and so as I personally share my own little story, the formula there never worked too well for me. So I'll just always stay with that integral, with that indefinite integral route as a separate work. And then on top of that, once I found this capital F prime of x successfully, I'll just go ahead and apply the fundamental theorem of calculus. Okay, and so in that way, here's how we find f. See, so capital F, we're on our way to find that. Okay, and so yes, so now x times sine of x. So this is trig function in that family, and then the x here is the algebraic function. So according to the Liate guide or the Liate guidance, then trig function comes after the algebraic family. And so that means now the u choice should be chosen for x. Okay, that's for our u choice. So that means now du dx must equal 1. Or in other words, du equals dx. Okay, and then once we have made our u choice, then everything else in this product, x times sine of x times dx, everything else aside from this chosen u choice, and everything else is a dv. So dv here is sine of x dx. So hey, it seems to be the example seems to be a different kind of example that shows how to handle a definite integral, but in the end it's another practice for anyone viewing the video about how we apply the integration by parts on an indefinite integral. Okay, and then once we're successful on this, then we're going to have a one small next step, substituting in the two integral bounds. Okay, so from here, v will be the integral of sine of x dx, which will give me negative cosine of x. And we don't need the plus c here. Okay, and so now, so any of this can exist in your written work. It can exist in some corner of your written work right there. And so in that way, now u times v, so this will turn into x times, so negative x times cosine of x, because x times minus cosine of x will give me minus x cosine of x. And then I will need to, I need a little more space for myself. I will need to do a subtraction. And then what we're having next here is going to be v du according to the integration by parts formula, v du. So v is here minus cosine of x, but du is just simply dx. So it's a minus from the formula, but then the integral here has minus cosine of x dx. Okay, and so in that way, minus x cosine of x minus with minus, it's become really a plus, an extra integral cosine of x dx. Okay, and so now this integral, this little integral that we produce, as an extra part throughout our integration by parts formula, is going to be a simple one. So our final answer for this is minus x cosine of x plus cosine of x, sine of x actually. Sine of x, okay? And then, of course, I was about to write down the plus c, but think about the further step, the step that's beyond this. We're not ultimately ending up with an antiderivative. We're only using this as a one big step, but to be ready for the next step, plugging in the two values here. And so in this particular problem, again, here's another instance, another occasion where I can skip the plus c right here, because this is not our final answer. We only use this general antiderivative, one antiderivative here to apply the fundamental theorem of calculus. And so now I'm going to go back to my other board, supposedly the continuation of our current work. All right, so that means in the end, this integral, the integral from 0 to pi x sine of x dx is equal to, now all that's minus x cosine of x plus sine of x that we have found previously. Okay, so I should use a double arrow to indicate that after we have found this separately as a as an antiderivative. So capital F of x right here, and then we did all the work that involves integration by parts. And when we came to our successful antiderivative, then I used that antiderivative. So the double arrow here is a consequence. So consequently, this beginning, which was a definite integral, will equal to the antiderivative that we have found just now and evaluated at 0 to pi. And now we will be able to evaluate that in a much more successful way over here. So what I'm seeing now, that answer is going to be minus pi times cosine of pi plus sine of pi, okay, and that's one of it, okay, and I'm going to subtract, okay, and then here we're looking at another open parentheses minus 0 times cosine of 0, okay, plus sine of 0, okay. Now this term here, anyone in a calculus class should be well familiar that sine of 0 is 0, so I cross it out because it means it's a 0 value. This is also a 0 value, okay. So cosine of pi is negative 1, but negative 1 times negative pi gives me a positive pi here in this whole first term, and then cosine of 0, but multiply with 0, so all that whole term here vanish, okay. So we only just have our final answer here being a pi. So just like how it has always been, definite integral will come out with final answer being a numerical value, where antiderivative or indefinite integral will only come out as an expression, as a function in the end, okay. But that is how we have done. That is how we have done, you know, a definite integral problem using integration by parts formula. So I mostly want my students, mostly want to pass this understanding of mine down to my students, that anytime you're handling this, keep it on the simple side, that just handle this definite integral problem first as a separate indefinite integral problem, where if you had to use integration by parts, then use it, okay, as a separate step. And then once you've found your antiderivative or the indefinite integral successfully, then you can, on top of that, we are going to apply the fundamental theorem of calculus that Isaac Newton has passed down to us right here. Okay, and that's how we have done example 2. All right, so now allow me to at this point of the video lesson right here, you have your choice of you have learned enough, but it is good that for a student at the calculus level to be able to see some proof, even though I am not going to deliver the formal proof for this. In the back of any of your standard calculus textbook, there should also be a well written out proof, but here I can just give a quick sketch of the proof of where the integration by parts, the formula came from. Okay. But so now, just as I promised earlier in the beginning of this video lesson, then why is it called a by parts? Why is it called by parts? Because see, UdV, okay, the first thing is that we have to be able to isolate our starting integral into different parts. There's a u part and there's a dv part. Okay, that's from our beginning problem. And then once we have had that, then you see we work on the u separately. I mean, that's a choice of ours, but we found the v parts separately. So that was something that we can find on our own right here. So each one of these parts, we found them for ourselves. So that's why it's called integration by parts. And then we produce another extra parts where we kind of swapped the role around a little bit. So the u here in the next part here is a dv, a du. And then there's a v right here. So that's why it's kind of called, intuitively it's called the by parts, because first we have to recognize there's one part for u, there's one part for dv, and consequently the u part is here, and the dv part gives us that v in part in this first term. and then they swap the rule. I mean, they swap their roles about there's a v part in the extra integral and there's the du part. So it's all about broken up into, well, it's two terms, and it's all, each term here, it comes from two separate parts and always stays together. Like say there's a u right here that we chose, and then there's the dv parts. Okay, and then these produce a consequence that there's a du right here, and then thus dv produce the v part in our next step. And that's why it's called the bi parts, okay? All right, but anyway, where did this formula come out from? And then, so let's have a quick little sketch of the proof right here. I'm not going to go through the formal proof because, and like I said, in the back of any calculus textbooks, right, there should be the proof for this being delivered, okay? So here's how I see it. Now, you have to recall your understanding back in differential calculus a little bit, those days where you were doing derivatives. Now, if you have two functions, in the end, u and v, they are functions. So if we have two functions in a product, and we take the derivative, then the product rule says taking the derivative of a product gives me u prime times v plus u times v prime. Okay, you can feel free to pause the video to remind yourself about the product rule back in those days that you were doing differential calculus, the kind of calculus work that you were doing derivatives all day. Okay, and so that was the famous product rule. And this is, right now, I'm taking you back to that point where we just completely having nothing to do with integral. And then think about this. If that was the derivative, then the left-hand side of the derivative of the product equal to the right-hand side of the derivative of these two terms right here. The first term has the derivative of u times v without derivative. And then the next term here, plus, right, u without derivative times v prime, derivative of v. So that means, and of course, all of these in the end is just assume in our simplest level in terms of variable x, okay? In terms of the variable x, so u is a function of x, v is a function of x, and then that is a function of x, u prime is in terms of x, and v is they're all in terms of x. So we can multiply, at this point, we can multiply the differential dx on both sides. Okay, the differential dx on both sides right here. And at this point, like I said, you know, at the end of your differential calculus course right here, then your instructor, including me, should have had some discussion to clear up the idea that we have dv dx to be the derivative of the function v in terms of x, or here we have du dx, but in the end, any of these can be regarded as a fraction. Okay, any of those can be regarded as a fraction between the two differentials. So in that way, now if I multiply the differential dx here, then nothing much to be done on the left-hand side. It's still a derivative of the product, u times v. That's the derivative, but multiply with the differential dx. And then here I can distribute this dx into each term, and that gives me u prime v dx plus u v prime dx. Okay, and then that's what it happened so far algebraically. After I multiply the dx to each term, and now the while step is going to happen ahead of time right here. I actually realized to myself I shouldn't rush into this step, distributing out that dx. I should have just allowed me to pull back to the step before. I apologize for a little bit of a confusion right here, but just right from this step, before I distribute out the dx right here, then this is what we can see. Now I can take the integral. So now the integral work comes in. Okay, I check the integrals both sides. So if you have a closed observation, this is a legal integral to do. Okay, it's a legal integral to do. And this is also a completely illegal. Think of all that expression here before the dx expression here as some derivative that involves two terms. Each term has some little derivative. Okay, And so now, on this left-hand side, if we take the antiderivative of this derivative, take antiderivative of that derivative in respect to x, and then this derivative is the derivative on the product, then don't we just simply get u times v, just it? Okay, nothing fancy. No, u times v, that's all it needs. The right-hand side here has two terms. And so now I can go ahead and break that into, see, the rule, the sum rule of taking antiderivative or taking indefinite integral allows me to break this down as a u prime v times dx plus a separate integral of u v prime dx. Okay, but so now I want you to understand this u prime v dx right here. We can, it's in the end these are all products. Okay, we can go ahead and turn the order of these two factors a little bit. I mean, multiplication is completely commutative. Big term. It just means we can swap the order of the multiplication. So v prime, I mean u prime times v is the same as v times u prime. So if you're writing this as the integral of a, if you're writing this purposely as a v times u prime right here, okay, and then times dx, then now here's what's going to happen. I see that u times v on the left-hand side equals, first integral is the same as v, and all that here is a du. Okay, that's v du plus, and the next one here, see, this v prime dx, right, including the dx expression, I call that it's the dv, and then this here is u. Okay, and so now at this step right here, what's my intention? We are right around the corner. Let me move over to the other board. All right, so at this point, after seeing that u times v is simply equal to two separate integrals, v du plus an integral of u dv, then I am simply going to subtract this to the other side algebraically. So that means now u minus, I mean u times v, subtract this term as an integral, v du, that will equal u dv. And ladies and gentlemen, if we're having a look closely at this final step right here, it is our famous integration by parts formula. U dv equals u times v minus v du. Okay, and so when I was teaching in my video lesson for the substitution method, I was saying out that the substitution method is the undo, or in case I didn't say that in that video lesson, it is worth it to mention the substitution method is the reverse operation of the chain rule back in the derivative state. But the integration by parts formula here is the undo, is the reverse of the product rule. Okay, the reverse of the product rule. Okay, but that's a quick sketch of the integration by parts formula, and that's how we arrived at that. And all of these formal, I mean, all the formal written steps can be offered, I believe, throughout any standard calculus textbook. But that's all. Anyone can. That should be good enough for anyone learning about the main idea, the core idea of how to find an antiderivative, how to find an indefinite integral using the integration by parts technique right here. So outside of this video, I will be, as I said, I will be having other little video clips right there where I deliver separate discrete examples. And of course, after this particular lecture right here, then you should be able to pick up the LIATE guide right there. So in other video lessons, in other video clips where I only mention about the examples, then when you view those videos, you won't be shocked. you won't be surprised about how I mentioned the term the Liate, because the explanation of the Liate is in this video lesson right there.